Have you ever found yourself wrestling with complex 3D modeling software, wishing you could just sort of tell a computer what you want to create?
Oh, absolutely. And have it appear fully editable right there on your screen.
Yeah, exactly. Because for AI researchers, for ML engineers, creating detailed, editable 3D assets is often this huge bottleneck.
It really is. Traditional methods, they demand very specialized skills or, endless manual tweaking.
Or you're training on these rigid 3D data sets, and the results are often hard to modify, hard to integrate. They just feel clunky.
Right, you're often stuck just manipulating raw mesh data, vertices and faces, which is precise, sure, but it has zero semantic understanding.
It's like trying to edit a document by moving individual pixels.
Exactly, instead of modifying the text. Or you rely on these models that generate static geometry from huge data sets, and they become black boxes. You can't easily refine them for what you actually need.
Well, welcome everyone to AI Paper Podcasts. Today we're digging into a paper that offers a really novel approach to this whole problem.
It's called LL3M, Large Language 3D Modelers, and it's by Signing Liu and the team at the University of Chicago.
And this isn't just some small improvement, is it? It feels like a fundamental rethink of how we could interact with 3D design.
It really does. Okay, so for a quick, 1-minute summary for everyone listening, LL3M is this groundbreaking multi-agent system. It uses large language models, LLMs, to generate and edit 3D assets.
Right, and the revolutionary part is the how.
Yeah.
Instead of learning from massive 3D data sets like we usually see.
Yeah, LL3M reimagines 3D generation as a code writing task. It actually produces interpretable Python code specifically for Blender.
And that shift changes everything. It unlocks incredible modularity, real editability, and it fits right into existing artist workflows.
You can interactively create shapes from scratch. You can make complex, precise changes using just natural language.
And crucially, it's not a one-shot deal. It supports iterative refinement. It's this co-creative loop between you, the user, and the AI.
Which is exactly what's been missing. That persistent problem of generating editable 3D geometry at scale has been a massive hurdle.
Yeah, existing methods, like you said, they rely on low-level stuff or specific data sets, and the outputs lack control. They don't play well with other tools.
And they're hard to interpret. You can't easily tweak them. They're like static snapshots, not flexible building blocks.
So this paper's core idea, it asks this really provocative question. Can pre-trained LLMs generate 3D assets just by writing code?
Exactly. Moving away from direct mesh generation to leverage the abstraction, the reusability you get with code.
They have that great example, right? A function for a Bezier curve.
Yeah. It can be reused for totally different things. A vase handle, a lamp wire, the legs on a chair.
The code is modular, reusable, and honestly, much easier for a human to understand.
And this is where LL3M really stands out from, previous work. Some earlier attempts used LLMs with Blender code.
Right, but more for retrieving assets or setting parameters in predefined scenes, maybe?
Yeah, exactly. LL3M goes way further. It generates comprehensive, open vocabulary 3D assets from scratch. That includes detailed geometry and appearance attributes.
And critically, without needing specialized 3D data sets or fine-tuning the LLM itself.
That's a huge leap, a really significant step up in capability.
Okay, so how does LL3M actually pull this off? You mentioned a multi-agent framework.
Yeah, think of it like a specialized team of AI agents, all LLMs, working together. Each one has a distinct role.
So like a division of labor.
Precisely. There's a planner agent that breaks down the task. There's a retrieval agent digging up useful info, a coding agent writing the actual Blender Python script.
And debugging visual evaluation.
Yep, a debugging agent and a visual evaluation agent for refinement, too. It's this sophisticated orchestration of AI skills.
That sounds complex. How do they coordinate?
So a really critical design choice here is the shared code context across all the agents.
Meaning they all see the same script.
Exactly. Every agent knows the previous attempts, the current state of the code. This allows for really precise localized edits.
Ah, so instead of starting over every time there's a change or an error.
Right. Which would be incredibly inefficient and totally break that iterative co-creative flow you want.
Okay, and you mentioned a retrieval agent. Where does it get its information? This sounds important.
It is. They did something called Blender RAG. It's not just a name, it's a retrieval-augmented generation knowledge base.
Built from what?
Directly from Blender's own extensive API documentation. They took 1,729 official Blender 4.4 HTML files and converted them into a searchable format.
Wow, okay, so it's grounded in the actual Blender documentation.
Yes, and BlenderRag is crucial. It injects precise, up-to-date info about writing correct, efficient Blender code. It gives concrete examples for advanced stuff.
So it makes the LLM better at writing Blender code without actually retraining it on Blender code.
Exactly. It significantly enhances the LLM's abilities while making sure the code is actually executable and robust.
And there are metrics on this, right?
Oh yeah, the results are pretty striking. The paper shows BlenderRag leads to a 5 times increase in unique complex Blender operations used.
5 times. And does that mean more errors? Usually complexity adds errors.
Remarkably, no. It also led to a 26% reduction in total code execution errors.
Okay, let that sink in. Using more sophisticated operations leads to fewer errors.
And higher quality outputs. The paper shows how BlenderRag enables things like intricate windmill details, complex geometry for like a Chinese lantern or a rocket with just the right glossy material.
Details that would be really hard to get otherwise.
Very difficult without that rich contextual documentation guiding the code generation.
Okay, so walk us through the actual process. How does an asset get generated? You said 3 phases.
Right. Phase 1 is the initial creation phase. So you give it a prompt, maybe create a red bucket.
Simple enough.
The planner agent takes that and breaks it down into subtasks. Then the retrieval agent queries BlenderRag for relevant docs or, code snippets.
It's helping the coding agent.
Exactly. The coding agent then writes and executes the Blender Python code, referencing those subtasks and the retrieved info.
And this handles things like API changes in Blender.
It does. Like if a parameter name changes, say specular becomes specular IOR level in Blender 4.x, BlenderRag helps the coding agent figure that out.
Ah. So the output code is correct for the current Blender version.
Yes, error-free executable code. And the output at this stage is a preliminary asset, maybe a basic red cylinder for your bucket, or a very simple tree shape.
Got it. Just the basics. Then what? Phase 2.
Phase 2 is the automatic refinement phase. This is where the visual feedback loop kicks in.
Using what? A VLM?
Exactly. A critic agent, using a vision language model like Gemini, analyzes renders of that initial asset. It looks for visual problems.
Like disconnected parts or colors not matching the prompt.
Precisely. Disconnected geometry, visual attributes that don't align, and it proposes specific fixes.
And then the coding agent implements those fixes.
Right. But crucially, it modifies the existing script. It doesn't just regenerate the whole thing.
That's the key point again, the iterative modification.
Absolutely. Imagine if asking for a tweak meant getting a whole new, maybe completely different bucket. That's useless. There's also a verification agent, also VLM-driven, that checks if the fixes were applied correctly.
So this phase takes that basic cylinder
and turns it into something that looks much more like a bucket, maybe with a reflective plastic material, or it adds more leaves and branches to the tree, making it more plausible.
Okay, makes sense. Auto refinement based on visual critique. What's the final phase?
Phase 3 is the user-guided refinement phase. This is where the co-creation really happens.
So now I get involved.
Now you get involved. You provide additional instructions in natural language. The coding agent and verification agent work together to implement them.
And the flexibility here is large.
Immense. You can iteratively refine way beyond the first prompt. Think add lemons to that tree, or sculpt a smiley face on the hat. Change the blade material to gold.
Wow. And because the output is actual Blender code.
Exactly. It's human readable. You can also dive in and directly tweak parameters, knobs, sliders, drop-downs that the code exposes, maybe through geometry nodes or shader nodes.
So you get fine-grained control over color, texture direction, crown height, whatever.
It's total control. And it's efficient, too. The paper mentions that after the initial creation and auto-refinement, which might take around 10 minutes,
okay,
subsequent user edits average only about 38 seconds.
38 seconds, even for complex stuff.
Even for edits needing maybe 3 or 4 follow-up prompts, it's still vastly faster than starting over from scratch.
That's impressive speed for iteration. Does it understand more complex ideas too?
It shows pretty impressive semantic understanding. For example, handling ambiguous instructions like change the style to steampunk.
How does it do that?
It applies consistent stylistic elements, gears, pipes, brass materials across different initial shapes, or interpreting eating the ice cream.
What does it do there?
It doesn't just move the ice cream near the mouth, it actually adjusts the character's pupils to look down at the ice cream.
Whoa, that's a subtle detail suggesting real understanding.
It's a level of interpretive depth you don't often see.
Okay, so let's talk about LL3M's overall properties. You mentioned versatility.
Yeah, the generality and versatility are really striking. The paper has this gallery of results: skateboards, drum kits, pianos, rockets, even dragons, all with intricate details, rich appearances.
And it handles variations well.
It does. Give it a generic prompt like a tree, and it can generate several plausible, distinct variations, all high quality. It's not just single objects either. It can take image inputs and generate whole scenes.
With multiple objects and coherent layouts.
Yes, maintaining spatial relationships.
And the fidelity. How close does it stick to the prompt?
That auto-refinement phase really helps ensure high fidelity. There's that cool example of the rocket prompted as blasting off.
What did it do?
The system didn't just generate the rocket, it added a fire blast at the base, reflecting the action in the prompt. It's understanding the context, not just the object.
That's pretty smart.
Yeah.
But he said the code itself is a key differentiator.
Absolutely. The structured and interpretable code it produces. This is huge for technical users, for you listening.
How so?
If you look at the code generated, say for a piano key, it's not just a jumble. It has comments, intuitive variable names, clear logic.
So even if I'm not a Blender Python expert.
You can probably understand what it's doing and maybe even modify it. This interpretability allows for really precise local edits without accidentally messing up other parts in the model.
Which is crucial when you're refining something complex.
Definitely.
Yeah.
How does it stack up against other methods? They compared it to Blender MCP, right?
Yes, and the qualitative comparisons in the paper show LL3M's output is, well, clearly superior.
Richer details, greater plausibility.
Yeah, things like correctly oriented cat whiskers, or a strawberry that actually has seeds modeled. It's attributed directly to that multi-agent design working together.
Makes sense. Did they test the importance of each agent?
They did an agent ablation study. It visually shows what happens if you remove each agent type.
Yeah.
Without the planner, you get fewer distinct parts. Without the retrieval agent, BlenderRag, the geometry is much simpler. Think scissors without proper blades, or a brush without hairs.
And the critic?
Without the critic agent, the overall visual quality just isn't as good. It really highlights that each agent adds something meaningful to get that final high-quality result.
Okay, it sounds incredibly powerful, but no system is perfect. What are the limitations? Right, they acknowledge limitations. Even with auto-refinement, sometimes spatial artifacts might persist, like a watering can handle that isn't quite connected.
Why does that happen?
Mostly due to the current limitations of the vision language models used for the critique. They might miss subtle geometric errors sometimes.
But there's a solution.
Yes, and this is key. That's where the user-guided refinement phase comes in again. You, the user, can easily spot that disconnected handle and just tell the system, connect the handle to the can.
So the human-in-the-loop aspect provides the final layer of correction. It's part of the co-creative process.
Exactly. It turns a potential weakness into just another step in the collaborative workflow.
Okay, so let's bring it all together. LL3M seems like a genuinely innovative system.
It really is. Transforming text descriptions into editable, high-quality 3D assets for Blender by generating interpretable Python code.
And it's not limited by object type. Handles geometry, materials, textures.
Yeah, a wide range of shapes, styles, materials. It's quite comprehensive.
So why should this matter specifically to, the technical folks listening, the AI researchers, the ML engineers?
Well, for technical professionals like you, this system could seriously change your workflow. Think about rapid prototyping for visualizations or iterating on 3D models for simulations or training data.
With unprecedented ease, just using language.
Precisely. It bridges that gap between a high-level creative or technical idea and the complex execution needed to realize it in 3D. It could massively speed up research visualization or content production pipelines.
It really lowers the barrier to entry for complex 3D work.
It absolutely does.
So, as a final thought for everyone listening to mull over, what if this whole code as 3D asset idea really takes off? How might it change the future of design, of digital content creation?
It's a fascinating question. Could we see a future where 3D modeling becomes as accessible, as iterative, as just writing a document, or maybe programming a simple script?
A world where researchers visualizing complex data or artists building virtual worlds can just use text prompts to build sophisticated 3D environments.
Empowering almost anyone. It shifts the focus, right? It's not just about generating shapes anymore. It's about generating understanding and control within the 3D space.
Giving us the power to build in entirely new dimensions just by describing what we want. Pretty profound stuff.
Definitely something to think about.